Hi, this is part 7 of this training video. Again, we're going to talk about the conceptual, mathematical, and computational models behind VZMOD. And you have seen this picture before. Again, this VZMOD simulate 1D unsaturated flow from dream field to water table, and also the ammonium and nitrate transport and reaction, which are absorption, nitrification, and denitrification. So for the 1D flow, you're gonna simulate essentially a vertical flow and steady state flow from dream field to water table. So this is the, and by the way, all the information you can find from the user manual of VZMOD. This is the Garmin equation, so I will not explain the detail of this, but essentially, again, this is 1D vertical flow and steady state. There's no time in this equation. And here H is the, we call it hydraulic head, and C is the elevation or depths. And this HLR is actually our top boundary condition. We call it hydraulic loading rate. That's how much water entering from septic tank to the vital zone. And also at the bottom boundary condition is water table, and you need a depth to water table to see tell the computer to what depths you're gonna simulate the unsaturated flow. And we have a number of parameters here. Those are essentially from the Van Opten model. That's essentially for soil physics, and this you will need this to simulate something called water retention curve, and those are diagram of water retention curve for sand, silt loam, and clay. And you see this is essentially tells the computer how much water will be kept in the soil, or on the other way, how fast the water gonna move from drain field to water table, right? So for this simulation, and they are closely related to the parameter we set up in the VZMOD. So this is again the interface of VZMOD. You need to specify the soil type, because again, different soil type gonna have a different water retention curves, right? And then for this top boundary, you need to specify the hydraulic loading rate, which is right here. This is 20, means 20 cubic meter per day, or something like that. So you can change it for different value that you believe appropriate for your simulation, and those things can be changed. Say it can be 20, and there's no problem for changing it. And then you need to tell the bottom boundary, essentially where the water table is. That's your DTW, 150 centimeter from drain field to water table, right? And those parameters right here are for flow simulation. Again, for different soil type, you have different values, right? So put sand here, and then we move to the next one is for reactions. And for ammonium and nitrate, when we consider three kinds of reactions. So one is, excuse me. So one reaction is, let's say there are two reactions are associated with ammonium. One is absorption, the other is nitrification. So absorption means, here's a diagram I have. So you have ammonium, which is positively charged, and you have a soil particle which is negatively charged. So that's why ammonium is absorbed on soil, because they have a different charge. So when we simulate the absorption, we use the linear isotherm absorption. That means this is the amount of the concentration absorbed on soil surface, and this is concentration of ammonium, in this case in water, right? So it just keep increasing. You have more ammonium, you have a higher absorption, and this is linear, could be infinite. For our case, because the concentration is always low, and so we there should be no problem to use linear isothermal. But if you say it's too high and you don't want absorption is too much, you can use Langmuir absorption. So we don't have this Langmuir and fluoride-rich absorption, but it can be added. So for simulating absorption, you will need tell the VZMOD was the absorption coefficient and was the soil bulk density. Soil bulk density to calculate how much absorption is. You have concentration, you have to multiply by the mass in order to get the mass of absorption, the mass of soil, and then you get the mass of absorption, mass of ammonium. So coming back to the VZMOD, so those are two parameters we just talked about. KD is for absorption coefficient, and rho is for bulk density. This is a bulk density, not particle density, so be careful about that. And then for ammonium, for nitrification, this is a reaction of ammonium nitrification. Essentially, ammonium become a nitrate, and this looks a simple reaction, but it's actually pretty complicated because those are actually biogeochemical reactions. You need bacteria to go through several steps from ammonium to nitrate, but we put it in a simple way. And you see, this reaction require oxygen. That means this reaction happens in aerobic condition, which is perfectly fine for soil because in soil particles you have water and air, so the nitrification is going to occur. And to simulate this reaction, we use the first order kinetics. So that means the nitrate ammonium concentration changes with time, and it's proportional to concentration of ammonium with those coefficients. And there are three coefficients here. So one is the KNINT, that's the maximum rate when everything is optimum. You have the right temperature, right moisture content, right nutrient for bacteria to convert ammonium into nitrate. But this rate is not, this condition are not optimum in real case. It may depend on temperature, and it may also depend on the soil water content. And let's say if it's too hot, the bacteria may not be active. It's too cold, it may not be active. So this is we call the correction factor, and this take into account of temperature impact, right? So this is the temperature of real world, and this is optimal temperature, and there's exponential function right here. And for the correction factor of soil water content, it takes this form. So it's essentially a step function for different degree of saturation. It behave in different way, right? So you see, we have a number of parameters here, and those are also related to the VZMOD. Let's go back to the VZMOD. So here you see we have a optimum temperature, which is right here, and we have a real world temperature, which is here, and then we have E2, E3, SH, SL, SWP, wilting point, and so on and so forth, and those are all here, right? Essentially, we got those values from StuMod. I mentioned that before, developed by the research group of John McCrae in Colorado School of Mine. And you can use them. I think you can feel pretty confident to use them, but if you have your own value, you definitely are free to change them, right? And this is an illustration of the nitrification. Say we have this initial concentration of ammonium. This is just illustration, which is 60 in the drain field, and the liquid out of the drain field, and it's 60, and then this is soil, there is oxygen, and so ammonium become nitrate, and that's why the concentration just decrease gradually, right? For nitrate, we have only one reaction. There's no absorption because nitrate is negatively charged, and your soil particle is negatively charged. There is a absorption of nitrate, and there is only one reaction, which is a denitrification, and essentially that means the bacteria gonna eat nitrate, and also use carbon as electron acceptor, and then convert nitrate into nitrogen gas. And this reaction occurs in anaerobic condition. So if it's aerobic condition, this will not occur because oxygen will take all the electron, and so this reaction will not occur, right? And so this is how we model it. So you have a nitrate concentration, and it has two parts. One comes from nitrification, right? So here, this is exactly the same. This is minus sign means ammonium is gone, but its positive sign means nitrate, ammonium become nitrate. And this is nitrification of ammonium, and this is denitrification of nitrate, right? And again, it has this maximum rate, and it's a function of time. And you have a correction factor for temperature, which is the same as we used before. And also you have a correction factor for soil water content, and this one is simpler than what you saw here for nitrification, right? And so this is related to the parameters we have for VZMOD. Again, you have optimum temperature, and this two could be different. This is for nitrification, this is for denitrification, and then you have the maximum rate, and you have a E1 value and beta value right here, and then you have your SDNT value, and then you input all here, right? So this is for nitrification. So and this is the diagram for nitrate, and you can see things a little bit weird here, right? So ammonium become nitrate, so ammonium concentration decrease with depths, and nitrate concentration increase with depths, right? But at here you see it nitrate concentration actually decrease. The reason of decreasing is that in this area, this is very special area for soil. So this is water table, right? So above water table is unsaturated, so the pressure is negative, but the water content is saturated at this very thin layer. There's a name for it, I just forgot it. So in this thin layer, pressure is negative, but water is saturated, right? Because water is saturated, this above this layer is aerobic condition, but beneath this layer or within this thin layer is anaerobic condition. So denitrification occur in this thin layer, right? That's why nitrate concentration decrease maybe slightly in this layer. So there's a physical meaning for this, right? So after we have that, after we consider reaction, so here let me give you a summary. So you have ammonium and nitrate coming from drain field, and then we consider the absorption of ammonium on soil particle, and we have dissolved ammonium in soil pores, and both of them go through nitrification process, become nitrate. And then if its nitrification is completed, there will be only nitrate coming into groundwater. But if nitrification is incomplete, you will have both ammonium and nitrate coming into groundwater. So this is overview of this reaction in the VZMOD. And then we have to consider transport, because there is not only reaction, and the ammonium nitrate also move with water. So as what we did for ArcNLET, we consider advection. That means your ammonium or nitrate move with water downward from drain field to water table. We also consider dispersion. This is 1D only. This is not 2D as in ArcNLET, but 1D dispersion. That means it disperses in the longitudinal direction. We have only D here. And then for ammonium, we have nitrate. Minus sign means it's gone from ammonium is gone, become nitrate. That's why I have a positive sign here. And then for nitrate, it has denitrification, right? So those are we call it reactive transport, because you have reaction and you have transport. And for this reactive transport, or we have those parameters. Look at this. We have D needed for the dispersion, and then the Q here, which is simulated by the flow, and it's already taken care of by VZMOD. And those are reactions we have, and those are concentration at the drain field, beneath the drain field, right? So these are the essentially what those parameters for used in VZMOD. And so this is a short video, but from here we're gonna talk about how to integrate them together. We already talked about ArcNLET for nitrate only in groundwater. We also already talk about the VZMOD for simulating ammonium and nitrate in the video zone. So now let's go back to ArcNLET to see how these two parts are integrated and how we add ammonium in groundwater. So that we're gonna talk about in part 8 of this training video. We're gonna see you there.